So last time we looked at how wires carrying currents can produce magnetic fields. Now in this case we have a coil, which is simply a wire that has a lot of turns in it. And since this coil is basically a wire, it will induce small magnetic fields around the wire. And this is throughout the entire coil. And what will happen is these small magnetic fields will accumulate to produce a magnetic field line that looks like this. So it's quite interesting how these little small magnetic fields can produce a magnetic field that looks like this. So let's look at the definition of something called the magnetic flux. Now we know that this coil will induce a magnetic B field, and the magnetic flux is the strength of the magnetic field within a turn. So in this one turn here, this one turn has an area A, let's say. The magnetic flux in that area is given by B times A, and it has a unit of something called Webers, which is denoted by this WB. Now there is something called the magnetic flux linkage, and I'm going to give it with this symbol here. And this is the total field strength in a coil. So this coil has n number of turns, let's say. The magnetic flux linkage has the equation n times the magnetic flux, or you can say that it has this equation where it's equal to NBA, and its unit here is Weber turns. Now these are quite important definitions that we'll need to know for later. So let's say we have a coil and a regular bar magnet, and what I'm going to do is I'm going to drop this bar magnet through the coil. Now when the magnet is dropped into the coil, you can see that the magnetic field lines of the magnet will be cut, or you can say blocked, by the coil. So as this magnet is going to be dropped through this coil, you can see that this wire in the coil is going to pass through the magnetic field lines. And now the technical name for what's going on here is that there will be a rate of change of flux linkage through the coil. And as this happened, there's going to be some work done from the magnet on the coil. And we know that the voltage is equal to work done over charge. So therefore, as this happens, a voltage will get induced in the coil. And since we have a voltage, there will therefore be a current induced as well. And now Faraday's law says this: the induced voltage, or the induced EMF, sometimes it's called, is directly proportional to the rate of change in flux linkage. So that means when this magnet is dropped, the voltage is going to be equal to NBA over time, and is actually going to be equal to minus NBA over time. And we'll look at what the importance of this negative sign is in a minute. But we can see that if this magnet is dropped faster through the coil, there will be a smaller time, so therefore the induced voltage will be greater. Now the reason for this minus sign is due to Lenz's law. And Lenz's law states that the induced current in the coil opposes the magnetic field that caused it to get induced. And here's what that means. Well, as this magnet falls through the coil, the magnet induces a voltage. And because there's a voltage across the coil, a current is produced. And from what we learned last time, we know that currents induce a magnetic field. So this current produced in the coil will induce its own magnetic field. And the induced magnetic field will oppose the original magnetic field from the magnet. And that's what Lenz's law is. And the reason it's a thing is because otherwise you would simply just get an infinite amount of energy if you continually just dropped a magnet through a coil. Now the best piece of advice I can give you after watching that video is to go off and practice some past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.